Welcome, my dear students. So, today in this session, we will continue our lecture on the types of flow of liquid. So, first, next one is one dimensional flow. So, what is this one dimensional flow? As the name suggests, the flow will be restricted to one dimension. Practically, it is not possible to restrict in one direction, but we will consider only one axis. Okay, so one dimensional flow is the flow in which parameters such as velocity, pressure, density, viscosity, and temperature vary only in one direction, and the flow is function of only one coordinate axis. The flow is function of only one coordinate axis and time. The flow field is represented by streamlines which are straight and parallel. Fine. So streamline is flow which we discussed in earlier class is a type of one dimensional flow, right? So mathematically for one dimensional flow, what we can write? So u is the function of f of x, where x is the axis. Okay, and what about y? In y axis there is no flow, as it is only one dimensional, and also in z we are not considering in both in x and y and z direction. We are not considering. We are considering only in x direction. For example, so what is the velocity? So velocity is a function of f of x. So flow between parallel plates. See here the flow. So this is streamline flow and are parallel. So these are plates. The flow between them is one dimensional flow. Okay, u is equal to f of x, where u, v, w are the velocity components and x, y, z. So x, y, z are the axis, coordinate axis or directions respectively. So what we have? We have to restrict to one direction only. Either u is equal to f of x, or if you want to take u is equal to 0, then v is equal to f of y you can take. Or you don't want y direction also, then what you can take? W is equal to f of z. Okay, if we consider any one axis, then other two will be 0. I am trying to tell you that. Okay, so here x is considered, so u is equal to f of x value will be there. What about value in v and w? It will be 0. It will be 0 in both y axis and also z axis. So such type of flow is called as one dimensional flow. Second one is two dimensional flow. So this two-dimensional flow is the flow in which fluid parameters vary along two directions, and the flow is the function of two rectangular space coordinates, that is x and y axis and time. The flow field is represented by streamlines which are curves. So in the one-dimensional flow, it is also by streamlines, but they are parallel. But here in the flow field, they are streamlines, but they are curves. And here the space coordinate are x and y. You can take y and z or z and x, but whichever two dimension you are selecting, that value will be there, and the axis which you are not considering, that value will be 0. Okay, so mathematically how we can write? So u is a function of f1 of x comma y. V is a function of f2 of x comma y. Then what about z? W is function of 0. Okay, so u is a function of f of 1 of x comma y. V is a function of f2 of x comma y. Then w in the direction of z, we are not taking any coordinates, so it is 0. So this type of flow is called as two-dimensional flow. Next we see the examples. So viscous flow between the parallel plates. See, the streamlines are curved. So here see, they are streamlines means they are parallel, but they have the curved surface. They will have the curved surface like this. See here, you can see a flow over a spillway. See, so this flow over a spillway is a what? It is flowing like in front also, and it's also flowing in downward direction also. So it is two-dimensional flow. So u is equal to f1 of x, v is equal to f2 of x comma y, and W is equal to 0 because in Z direction there is no flow. So flow over a spillway is a clear example of two-dimensional flow. So next is our three-dimensional flow. So this three-dimensional flow is the flow in which flow parameters change in all the three directions, and the flow is the function of three mutually perpendicular coordinate axes. So here it will change in all the three directions with respect to the three mutually perpendicular coordinate axes and time. The streamlines are in space curves. So the streamlines are space curves. So mathematically, the three-dimensional flow value, how we can write: u is a function of f1 of x comma y comma z. V is a function of f2 of x comma y comma z. W is a function of f3 of x comma y comma z. Okay, so how we can show viscous flow in a duct? The three-dimensional flow, you can see here it is moving. This is already 2D, right? So it's also moving here, you can see here. So a flow in a pipe, that is viscous flow, can be regarded as a three-dimensional flow. So this type of flow is called as three-dimensional. One-dimensional, two-dimensional, three-dimensional. Here equations are important. So whenever three-dimensional flow we are talking, we have to take three directions. That is, u is equal to function of, u means the velocity of that particle in x direction. V is velocity of particle in y direction. W is velocity of that particle in z direction. So whenever we take three-dimensional, that is f1 is u is a function of x comma y comma z. If we take two-dimensional, u is a function of f1 comma x comma y. If we take one day, then u is equal to f1 of x. Like that it varies. Okay, next you can see an example for two-dimensional flow. So over a weir, as I already told you in spillway, so same type. Over a weir also we can tell it as a two-dimensional flow. So flow in three-dimensional, how we can see this is the dam, this is silting basin. So in this dam the water is collecting here from here. Okay, so this type of example we can give for the flow is three-dimensional. Fine. So next, so all the types of flow are over. Next we will come to the rate of flow or discharge. So what is this rate of flow or discharge? It is represented by the letter Q. Q is what? Discharge or rate of flow. So it is, the rate of flow is defined as the quantity of fluid flowing per second through a section of a pipe or a channel. Simply, the quantity of fluid passing through any section in a unit time. So quantity of fluid passing through any section, it may be pipe, whatever section we consider. Okay, so quantity of fluid passing through any section in a unit time or per unit time can be tell as the quantity or the rate of flow or discharge. So Q is, from now we will tell it with respect to it is discharge. So what is the unit? So 6 meter cube per second. So what is fluid is meter cube per second. So quantity of fluid passing through any section in unit time is regarded as meter cube per second. So its types are there. So if the volume flow rate, so when the volume flow rate for an incompressible fluid, the rate of flow or discharge for incompressible fluid, the rate of flow or discharge is expressed as the volume of fluid. So it is discharged as volume of fluid across the cross section per second. Whereas for compressible fluid, it is taken as weight flow rate, that is weight of fluid per unit time. If it is compressible, we have to will take as this weight flow rate. If it is incompressible, we will take as volume flow rate. Okay, and mass flow rate we can convert it to either or neither or, like that. Okay, so volume flow rate, mass flow rate, and weight flow rate. So what is the formula of Q? Q is equal to area into velocity. Q is equal to A into V. Whenever we come across mass flow rate, then it is equal to rho into Q or rho into A into V. Whenever we come weight flow rate, it is rho g into AV. So simply, what is discharge? Discharge is defined as the quantity of fluid flowing per second through a section of a pipe or a channel. You can tell like this. Next, area is where Q is defined as what? Area into velocity. This is the formula. Area into velocity. What is Q? Q is equal to Q means discharge. Discharge is equal to area into velocity. Next, we will come to continuity. So continuity equation. So what is continuity? So matter cannot be created or destroyed. Any matter in this universe cannot be created or destroyed. It simply changes from one form of the matter to another form of matter. So this principle is known as what? Conservation of mass. We already know this. So the mass can neither be created nor be destroyed, but it can be changed from one matter to another matter, right? This principle is known as conservation of mass. So here we use it in our flowing fluid analysis. Okay, the principle is applied to fixed volumes. The principle is applied to fixed volumes known as control volumes shown in figure. See, this is the control volume, the principle of conservation. So consider this as a control volume. Okay, it's just a volume. So what does the conservation of mass principle tells us means the mass entering per unit time, the mass of flow, this is entering in the control volume, right? So the mass entering per unit time, okay, is equal, or mass entering per unit time minus the mass leaving per unit time, the mass entering per unit time and the mass leaving per unit time is subtracting, the subtraction of that will get us the increase of mass in the control volume per unit time. Okay, so whatever the increase we are getting by this mass will flow in and this mass will go out, then in this process the volume remaining in this control volume, what does it mean? So whenever mass comes it increases, right? Increase of mass in control volume per unit time. So as it increases it also goes out also. So whatever the quantity here, it is neither it is not wasted, right? Just it is converting from one form to another form. Input is coming, output is going. So the conservation of mass is observed. So like this, you have conservation of energy. Energy can neither be created nor be destroyed, but it can be transferred from one form to another form, like that. So mass is also, matter cannot be created nor be destroyed, but it can be changed into different forms of matter. So from this conservation of mass, what we can write means, so mass entering per unit time, mass entering per unit time minus mass entering per unit time is equal to the total or the increase of mass in the control volume per unit time. So this is the general theory or general theme of this conservation of mass. Mass entering per unit time minus mass entering leaving per unit time is equal to increase in the control volume per unit time. So with this basic concept we'll find the continuity equation for our fluid flow. Okay, so now, so for steady flow, so what is the steady flow? As you remember in your last class, the steady flow is defined as what? The type of flow in which the fluid characteristics like velocity, pressure, density, etc. at a point do not change with time. The fluid parameters do not change with time. So thus, for steady flow, there is no increase in mass. There is no increase in mass within the control volume. Means what? So this increase of mass for steady flow, mass entering per unit time is equal to mass leaving per unit time. When it is zero, no? When it is zero, this minus will come this side and mass entering per unit time is equal to mass leaving per time. So for steady flow. So what is that telling? For the steady flow, there is no increase in the mass within the control volume. So mass entering per unit time is equal to mass leaving per unit time. So derivation, how we can consider? Let us consider stream tube. Stream tube consists of what? Streamlines only. So let at a section 1 1. So this may be the section 1 and this may be the section 2. Okay. So this is section 1 and this is section 2. Fine. So let rho 1 v1 a1, rho 1 density v1 velocity a1 is the area of that cross section, or mass density velocity and cross sectional area at section 1. Similarly, rho 2 v2 a2 are the mass density velocity and cross section at the area 2. This is section 1 1 and this is section 2 2. So according to the mass conservation energy, m1 mass entering per unit time. So whatever the mass entering per unit time, m1 minus m2, m1 minus m2 is equal to differentiation of the mass in the control volume with respect to time, right? But here, as this is a steady flow, this will be equal to 0. What is m1? Rho 1 a1 into v1. What is m2? Rho 2 a2 into v2, right? So rho 1 a1 v1 minus rho 2 a2 v2 is equal to differentiation of mass in the control volume with respect to time. Then when for steady flow it will be 0 na, then what it happens? So for steady flow condition, so differentiation of mass in control volume by dt is equal to 0. Then rho 1 a1 v1 minus rho 2 a2 v2 is equal to 0, which implies rho 1 a1 v1 is equal to rho 2 a2 v2. Okay, so this m is nothing but rho 1 a1 v1 is equal to rho 2 a2 v2. So mass is conserved, right? Hence for steady flow condition, mass flow rate at section 1 is equal to the mass flow rate at section 2. That is, mass flow rate is constant. Mass flow rate is constant if we consider what's g. Similarly, so rho 1 g a1 v1 is equal to rho 2 g a2 v2. So it will not change, just it will be add up. Assuming incompressible fluid. Incompressible fluid means what? The density will not change. Rho 1 rho 2 will be equal to rho. Incompressible fluid. Okay, so if it is incompressible fluid, what will happen? This rho 1 is equal to rho 2, then g equal to g. a1 v1 is equal to a2 v2. See here, a1 v1 is equal to a2 v2. What is this a1 v1? It is nothing but q1. What is a2 v2? q2. So q1 v1, q1 is equal to q2 is equal to q3 is equal to q4. Therefore, according to the mass conservation for steady flow of incompressible fluids, the volume flow rate remains same from section to section. So this is your continuity equation. Understood? So a1 v1 is equal to a2 v2 is your continuity equation, which is a very important formula in your coming classes. Okay, so q1 is equal to a1 v1 is q1 is equal to a1 v1, q2 is equal to a2 v2. Okay, now if this is asked in exam, how to write? Okay, you can't explain this theory of matter and all. So how to write means, I'll tell you. So you have to start like this. So the equation based upon the we'll take an equation based upon the conservation of mass is called as continuity equation. Next, draw this diagram. So thus for a fluid flow through pipe at all the cross section, the quantity fluid per second is constant. The quantity of fluid per second is constant. How this is constant? The quantity of fluid per second is constant by which law? By the law of principle of conservation of mass. So now we have to derive, no, consider two cross sections of pipe as shown in figure. So this is pipe. We are considering two cross section 1 1 and 2 2. Let v1 is the average velocity at section 1 1, rho 1 is the density at section 1 1, a1 is the density at section 8 1 1, and similarly v2 is the average velocity at cross section 2 2, rho 2 is the density at section 2 2, a2 is the area of the pipe at section 2 2. Like this we have to draw our diagram and we have to detail the information which is in the diagram. So what is this? we have to consider the fluid flowing through the pipe at the cross section. Fluid flowing through a pipe cross section. So then what we can do, then the rate of flow at section 1 1, the rate of flow at section 1 1, okay, is equal to, according to the conservation of mass, is what is equal to the rate of flow of fluid at section 2 2. Okay, so now the rate of flow of section 1 1 is what, rho 1 a1 v1. What is the rate of section 2 2? Rho 2 a2 v2. So according to the conservation of energy, so rho 1 a1 v1 is equal to rho 2 a2 v2. Okay, this equation is applicable to compressible as well as incompressible fluid in the continuity equation. If the fluid is incompressible, if the fluid is incompressible means what? The density are same, then it is equal to a1 v1 is equal to a2 v2. Okay, now I'll write that. See, then the rate of flow at section 1 1 is rho 1 a1 into v1. Rate of flow at section 2 2 is rho 2 a2 into v2. So according to the law of conservation of mass, the rate of flow at section 1 1 is equal to rate of flow at section 2 2. So rho 1 a1 v1 is equal to rho 2 a2 into v2. So this equation is applicable for both compressible and incompressible fluids. And this equation, equation number 5.2, is called as what? Continuity equation. But for incompressible fluid, the densities are same. Okay, the density would not change, so it will not change. So this rho 1 is equal to rho 2 will be equal to rho, and this will be cancelled. Then the continuity equation reduces to a1 v1 is equal to a2 v2. So this is about the continuity equation of this fluid flow in the pipe. Now let us solve a problem. Okay, simple problem. See, the diameter of a pipe at section 1 and 2 are, so the diameters of section, this is a section of a pipe. Okay, see here, concentrate, don't see the answers, see the image. It is given question. The diameters of a pipe at section 1 1 and 2 2 are given. So at diameter 1 1, at section 1 1 diameter is 10 centimeter, at section 2 2 diameter is 15 centimeter. So we have to find the discharge, we have to find the discharge Q. Okay, through the pipe if the velocity of water flowing through the pipe at section 1, so velocity is given for section 1, that is 5 meter per second. Determine also the velocity at section v2. So we have to find Q and also v2. Okay, so same fluid will flow now. Okay, the same fluid will flow through this section and this section, therefore it is incompressible fluid, that is density is equal to, density is same, so no need to consider the density from this figure, right? Now we will write the data. So what is the data given? So at d1 10 centimeter it is 0.1 meter. Okay, v1 is 5 meter per second. It is a pipe, so area is circular, so what is the area? Area is equal to pi d square by 4. Okay, so what is d1? 0.1, so pi d square by 4 is 0.07854 meter square. At section 2, d2 is 15 centimeter, is 0.15 meter, so a2 is pi d square by 4. Okay, we have to find v2. Fine. Now we can find discharge here, no, because we have the values of what? We have all the values, that is discharge through at section 1 1. What is that discharge? That is Q is equal to a into a1 into v1, right? So what is a1? A1 is, we know, 0.07854. v1 is what? 5 meter per second. So we got the discharge as this. Okay, so this is the discharge through that pipe. But according to the law of conservation of moment, or due to the or you can also tell that from the continuity equation, what is that? a1 v1 is equal to a2 v2. From the continuity equation, A1 V1 is equal to A2 V2. So what we want here? V2 we want. So V2 is equal to A1 V1 by A2. So A1 V1 is nothing but Q. So 0.007854 into 5, this is nothing but your value of Q divided by A2, 0.01767. So once we substitute, we will get direct substitution problem 2.22 meter per second. So easy problem will be there. Just you have to understand where you have to apply, what you have to apply. That's it. Only you have to use the continuity equation, that is A1 V1 is equal to A2 V2. So this is one type of problem. The second type of problem is, so it's also very easy. So now see, a 30 centimeter diameter pipe conveying water. So a pipe is there. It is 30 centimeter diameter of pipe conveying water, branches into two pipes. So the same pipe branches into two pipes. That is, one is 20 centimeter and one is 15 centimeter. So it branches as 20 centimeter and 15 centimeter. If the average velocity in the 30 centimeter diameter pipe, 30 centimeter diameter means mother pipe, okay, big pipe. 30 centimeter diameter pipe is 2.5 meter per second. So velocity here given as 2.5 meter per second. Find the discharge in this pipe. Okay. Also, we have to find what? Q. Find the discharge. Also determine the velocity in 15 meter centimeter per centimeter pipe if the average velocity in 20 centimeter diameter is 2 meter per second. So here V2 is given, but V3 we have to find. Correct? So this is our problem. We have to find Q and also V3. So what we can do, we'll do general discussion here. See, the what are the datas we know. So D1 is 30 centimeter, 0.30 meter, V1 is 2.5 meter per second. Okay. So V1, D1 we know, we can find what? A1. A1 is what? Pi by 4D square. That is D1 is 0.3 square. Okay. We'll calculate. Next, V2, D2 we know, we can find A2. Fine. Here we can find A3. No, we don't know the value of V3. We can't find A3. So once we got the value of A1 and A2, okay, we will apply our law of conservation of mass. What is that? According to the law of conservation of mass, what will happen? This volume of flow, ಇಲ್ಲೇನು ಫ್ಲೋ ಆಗ್ತಾ ಇದೆ ಲಿಕ್ವಿಡ್, ಇದೇ ಲಿಕ್ವಿಡ್ ತಾನೇ ಇಲ್ಲಿ ಹೋಗಿ ಇನ್ ದಿಸ್ ಹೋಗೋದು. ಓಕೆ, no different liquid will come. So the volume of liquid flowing, if Q is flowing here, this Q, some part of Q will go here and some part of Q will go here, right? So what I do is, the part of liquid going to the section 2 is I'll take as Q2. The part of fluid going to section 3 I'll take as Q3. Correct? From the law of conservation of mass, what will happen? This Q means this Q in the section 1 is equal to what? Q2 plus Q3. Correct? Q1 is equal to Q2 plus Q3. So what is Q1? A1 into V1. What is Q2? A2 into V2. What is Q3? A3 into V3. Correct? Now we have, first we will find the value of Q1, as we already have the value. Once we find the value of Q1, this is done. Next we will find the value of Q2. We will also get the value of Q2, but at Q3 we will not get the value of what? A3 into V3. Before that we have to find for V3, right? So when we know these values, we have to just use the mathematics and we have to solve for Q3. How? I'll show you now step by step. So see, D1 0.3 meter. First I clear this. So see, D1 is 0.3 meter. So A1 is 0.07068 meter square. V1 is 2.5 meter per second. So it is for the section 1. For the section 1 means the bigger mother pipe. Okay, big pipe. Next, D2, A2, V2. This is for the branch 2. Next D3, A3. D3 is there, A3S. We can find pi d square by 4. Yes, we can find A3. Just we have to find what? V3. Correct. Now, what find the discharge in pipe Q1 we have to find, and we have to find the velocity at 15 centimeter pipe or V3. What we can use? We can use directly the formula, that is Q1 is equal to Q2 plus Q3. So let Q1, Q2, Q3 are discharged in pipe 1, 2, 3. Then according to the continuity equation, Q1 is equal to Q2 plus Q3. So the discharge in Q1 in the pipe is given by Q1 A1 is equal to Q1 is equal to A1 into V1. So A1 into V1, we will get 0.1767 meter cube per second. So we got the value of Q1. One part of the problem is over. Now we have to find the V3. Okay. So Q2 is equal to what? A2 into V2. So we also got Q2. Substituting the values of Q1, Q2 in the main equation, that is Q1 is equal to Q2 plus Q3. So Q3 is, we know the value. Okay. Q1 is, we know the value. Q2 we know the value. Q3. So Q3 is equal to, once we substitute, we will get the value of Q3. So what is Q3? Q3 is equal to A3 into V3. We know the value of Q3 and also A3. So what is remaining? We have to find V3. So substitute and find the value of V3. So V3 is equal to Q3 by A3. It is 6.44 meter per second. Okay. Just all easy substitution problem will come. Just you have to think and you have to apply the concepts. That's it. So this is how problem may come from your continuity chapter or continuity topic. Next, we will see about the velocity. So what is velocity? We know velocity, what is velocity, but in the kinematics, we have to, in this chapter, we have to denote them with respect to time. So that thing we have to learn here. So let V is the resultant velocity at any point in the fluid flow. Okay. So V is the resultant velocity in the fluid flow. Let U, V, W are its component. U, V, W are what? U is the function, U is the velocity in x direction, V is the velocity in y direction, W is the velocity in z direction. So the velocity component are the function of space coordinates, that is x, y, z, and also time. Here we have to consider everything, every parameter with time. So mathematically the velocity components are given by how U is a function of f1 of x, y, x, y, z, t. So U is defined like this. V is also function of what? f2, f2e into, means function of x, y, z, t. W is also a function of x, y, z, t. Now resultant velocity, now we can write, so the resultant velocity is equal to this. We have to remember, resultant velocity is equal to V is equal to Ui plus Vj plus Wk. Resultant velocity is equal to V is equal to U into I plus V into J plus W into K. Or we can also find by square root of U square plus V square plus W square. So if it is given in the equation form, we have to use this. If we already have direct values of UVW, we have to use this to find the resultant velocity. To find the resultant velocity, we have to use this formula. What is that formula? If it is given in the equation, V is equal to Ui plus Vj plus Wk is equal to root of U square plus V square plus W square. It is the standard form. So it is helpful in our problems which comes related to the velocity. Next, once we know the velocity, what we can find? We can find acceleration. So here also acceleration we have to take in terms of respective direction. Let ax, ay, az are termed as total acceleration on respective direction. So the total acceleration has two components, that is, one acceleration is with respect to time and also another with respect to space, and can be expressed in terms of UVW. So acceleration in terms of x is equal to acceleration in terms of x is equal to, see here, one method is there to follow this. However, I tell you, just follow that. So acceleration in terms of x, right? In terms of x means what velocity will be there? U. So U is commanding. So note here, U is commanding. Everywhere in the numerical, U should come. Okay. So first we write with respect to what? Time. So what is that? Dou U by dou T. Dou U by dou T plus U into. So these are coming, no? So dou U by dou T plus U into dou U by dou X. So with respect to X. Next, dou U by dou Y with respect to Y. Next, W is equal to W into dou U by dou Z with respect to Z. So like this, we have to do for every directions. So if you want in AY, what we can write? First, we have to take with. So in Y direction, what is the velocity we are considering? That is dou V. So dou V by dou T, correct? Then plus, now with respect to space, so in the U direction, dou V by dou X. In a V in Y direction, V into D dou V by dou Y. In Z direction, W into dou V by dou Z. Okay, whenever we talk with respect to Y axis, here in the numericals we will get dou V, and others are same as in the first. So when we come to the Z direction, same dou W by dou T plus U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z. So this dou U by dou T, dou V by dou T and dou W by dou T is nothing but the local acceleration of the particle, and this is the connective acceleration. Okay, Euler's equations are applicable to compressible, incompressible and non-viscous and steady or unsteady flow of liquid. First, so these are the equations which we have to use when we do the problems. So for steady flow, what is the steady flow? It will not change with time. Okay, the velocity parameters will not change with time. If it will not change with time, then dou v by dou t is what? 0. Then v is what? Resultant velocity. Then dou u by dou t is equal to 0, dou v by dou t is equal to 0, dou w by dou t is equal to 0. Then the equation which we saw in the last this slide, no, this will be reduced to dou u by dou t is equal to u is equal to dou u by dou x plus v is equal to dou u by dou a plus w is equal to dou u by dou z. So in when we talk with respect to x, so u into dou u by dou x, numerical should be same. V into dou u by dou y, w is equal to dou u by dou z. Similarly for ay, dou v by dou x, u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. Similarly for az also, az is equal to differentiation of velocity with respect to w with respect to time, differentiation of w means velocity in z direction with respect to time is u into dw dou w by dou x, v into dou w by dou y plus w into dou w by dou z. Fine. Now this acceleration vector, how we can write? Ax plus ayj plus azk. This is very important. If they are given the equation, we have to compare with the standard equation. If you want to find the resultant value, then square root of ax square plus ay square plus az square. So these are the correct equations. These are the equations for which we have to compare with it. In the questions, they will directly give the equation. We have to compare with this, and we have to take the value of ax is what, ay is what, az is what. So once you will go enter the problem, we will come to understand. Fine. Now see, one problem is there. So the velocity vector in a fluid is given. Okay, so what is given? Directly they are given 4x cube I minus 10x square yj plus 2tk. So directly one velocity vector is given. So to solve this, what we have to know? We have to know the velocity vector formula, which I did. Wait, I'll show that. So here, So this velocity vector formula, what is that? Ui plus vj plus wk. So this is important. So we have to compare with this. Okay, once we compare with this, so v is equal to what? 4x cube I minus 10x square yj plus 2tk. Find the velocity acceleration of the fluid particle at 2, 1, 3 at a time t is equal to 1. So how is the solution? The velocity components of u, v, w are, so u is equal to what? 4x cube I. So what we are writing in the last where that u into I, right? U into I. What is the u value? 4x cube. Next, v is what? There plus vj is there. So here v is equal to minus 10x square into y. So w is what? W is equal to 2t. We comparing with the standard equation. Now for the point 2, 1, 3. So x value is 2, y value is 1, and z value is 3. Right. For this value, we have to calculate what is u, v, and w. So x is 2, y is 1, z is 3, and time is 1. So hence velocity components at 2, 1, 3 are u is equal to 32 units. Directly we are getting. So they will give to confuse you in the form of equation. They will also give what to substitute. Okay. Some people without this information, what they do, they just ignore this. But it's an easy problem, right? Just we have to substitute the given element with that standard equation. So u is equal to 32 units. V is equal to what? Minus 10x square into y. So minus 10 into 2 square into y. In the place of x, we have to put the value of 2. In the place of y, we have to put the value of 1. And the place of z, we have to put the value of 3. So w is what? 2t. So 2t is what? 1. 2 into 1, 2 units. So velocity vector at 2, 1, 3 is equal to what? Here we'll find the equation, that is 32i minus 40j plus 2k. So if we want to resultant velocity, so square root of u square plus v square plus w square, right? So it is velocity is what? 51.26 units. So directly comparing the velocity vector equation, we finding the value of resultant velocity. Easy, no? Then for acceleration velocity, we have to consider the same equation, that is ax equal to u into dou u by dou x. So this equation is there. So for this equation, we have to compare with this, and we have to write each and every value. Just you have to remember this. Okay, you know the tricks how to remember now. So substituting the values of dou u by dou x. Dou u by dou x is what? Differentiation of u. See, differentiate dou u by dou x means differentiation of this. That is, if we differentiate 4x cube, what will be there? For 12x square, right? If we differentiate dou u by dou y, it is 0, and dou u by dou z is also 0, because y and z term are not there. Concentrate here. What I am doing, I'll tell you. So I want the value of dou u by dou x, I want the value of dou u by dou y, I want the value of dou u by dou z. I have the value of u, v, and also w. What I am doing, I am differentiating with respect to x, y, z. Okay, so that I can have the values, and I'll substitute in this equation. Okay, now let me clear this. So u is equal to what we get? 4x cube, v is equal to minus 10x square y, and w is equal to 2t. So dou u by dou x, it will be 12x square, right? 12x square. Similarly, dou u by dou y, dou u by dou z will be 0, and dou u by dou t will also be equal to 0 only. Next, dou v by dou x. So dou v by dou x, what will be dou v by dou x? So dou v with respect to x, that is 20 minus 20xy. Dou v by dou x is minus 20x into y. Okay, dou v by dou y, yes, we can do. Y term is also there. What is that? Dou v by dou y is nothing but 10 into x square. Dou v by dou y is 10 into x square, right? Then dou v by dou z, z term idya illa, so 0. Okay, here when we come to w is equal to 2t. So w is dou w by dou x, so x term is not there, 0. Dou w by dou y term is not there, 0. Dou w by dou z term is not there, 0. Then dou w by dou t, yes, t term is there, so dou w by dou t is what, 2. Okay, so this is done here. So dou u by dou x is 12x square, dou u by dou z is 0. Everything is 0 in the first equation u. In the second equation v, dou v by dou x is minus 20xy, dou v by dou y is minus 10x square. So dou v by dou z and dou v by dou t is 0. So in the third equation, dou w by dou x, dou w by dou y, dou w by dou z are 0. So dou v with respect to time is what, 2. Okay, dou w by dou z is 2. Now printing mistake this is, okay, dou w by dou z is 2. Now we have to substitute this equation in this equation. We have to substitute the values of that equation in this equation. We will substitute now. See, substitute the values in acceleration components 2, 1, 3 at a time t1 r. So ax square is equal to, what is u? U is nothing but 4x cube. Next dou u by dou x, right? So sitting calm and you have to substitute one by one. So 4x u is dou u by dou x plus v into dou u by dou y plus w into dou u by dou w, correct, plus dou u by dou u by dou t. So when we substitute the values, we'll get 4x to the power of 5. So it's 1536 units. Similarly, when we substitute for ay, what is ay? So u into dou v by dou x plus dou v into dou v by dou y plus w into dou v by dou z plus 0. So ay is equal to 320 units. Please sit and please substitute one by one. You will get the values, pakka values. So once az, this all 0 we get, we will only have the values 2. So this is printing mistake. Okay, that is 2 units. So acceleration is what is the acceleration vector? Ax plus ax into I plus a y into j plus az into k. So substitute that values. 1536i plus 320j plus 2k is the acceleration in the form of vector. If you want resultant, a square plus b square, a square plus ay square plus az square, when we do that acceleration, we will get the value as 1568.9 units. So easy, right? Just we have to memorize the formula and we have to substitute. That's it. Only the work, calci work is there. Nothing conceptual or nothing, anything is there. Just you have to have some concept and you should be good in calculation. That's it. You can find the values and you will get the marks easy. Next, we'll come to the continuity equation in 3 dimensions. So this continuity equations in 3 dimensions I'll do in the next session. So for this session, I hope you understood the problems on the velocity and acceleration of the fluid flow. Okay, you must solve the problems in your home so that you will be practice, right? So these were the topics in today's session. So I hope you understand. Thank you.